Okay, we are looking at section 3.5, and here we're going to apply the derivatives to some story problems. So 3.5. Oh, let me get rid of this. Okay, we did talk about this stuff in chapter 1. If you have a distance time graph, some function f of x where we've got distance on the, say, feet, some kind of a distance on the vertical, and time and seconds on the x-axis. We want to talk about velocity and acceleration today. First of all, if you just look at the definition of velocity, velocity is defined as your change in rate of change of distance over time. So we're talking about the change in distance over the change in time, and because it's a rate of change, velocity is a derivative of distance. So velocity is the derivative of distance. And remember, just in general, if our derivatives are positive, that means your function's increasing. So if our velocity derivative is positive, that means our distance is increasing. If the velocity is negative, the distance is decreasing. So positive velocity means distance is increasing. Negative velocity just means distance is decreasing. Doesn't mean you're going slower, it's directional. The positive and negatives are directional. And speed doesn't take into account direction, it's the absolute value of velocity. And you may have talked about all of this stuff in physics before. I'm not sure if you did that yet. And so that makes speed always positive. So speed doesn't take into account direction. Now, acceleration. It's also a rate of change. So it's also a derivative. But this one is the rate of change of velocity over time. So it's the acceleration is the derivative of velocity. Or you could call it the second derivative of distance. So this is the first time we've talked about a second derivative, and we have notations to show that we're taking second derivative. The symbolism then would be like y double prime, or f double prime of x, or that other notation, that fractional notation, the dy dx, it would be d2 over dx2. Okay, I'm not sure why it's on the d there and on the x here. I don't know, just the way the notation goes. But all of these mean second derivative. So I want to talk about the units again, why they are what they are. So, well, velocity is the easy one. You know, it's like feet per second because you're taking the change in feet over the change in seconds. So the velocity graph, if I was to take the derivative of the original function, it's all increasing. Maybe it looks like this. This would be f prime of x, where I would have feet per second here, in seconds here. But now when I go to acceleration, I'm going to be doing derivative of these two units. And when we do derivative, we're dividing, because we're taking the change in velocity or the change in time. I'm not going to answer that. All right, let's see, where are we at? Oh, I was back on this. Sorry, I was listening to the message. Here we're going to take the change in velocity over change in time, so that's feet per second. Over seconds. And if you think of it as a fraction divided by a fraction, when you flip it over and multiply, you're going to get feet per second squared. And so those will be your units on acceleration, because you're taking the change in velocity over the change in time. Okay, now how can you tell if an object is speeding up without actually looking at it or seeing it? We can use these derivatives to tell us that. An object will be speeding up if both velocity and acceleration have the same sign. That means they're either both positive or they could both be negative, because remember, negative is just a direction. So if both signs are the same, your object is speeding up. So then, to tell if it's slowing down, if velocity and acceleration have opposite signs. So speeding up if they're both the same, slowing down if one's positive, one's negative. Alright, so the story problems today aren't too bad if you take your time and you really look to see what they're asking for. Is it velocity? Is it acceleration? Is it distance? So let's go through a couple. Example 1. The displacement of a punted football is given by the equation y equals negative 16 t squared plus 37t plus 3, where y is going to be the feet off the ground, and t is going to be the seconds since it was punted. So if we just take a quick look, if we put 0 in for the time, 0 there, 0 there, the football is starting 3 feet off the ground. So that would be the punter holding it out in front of them, 3 feet off the ground, and then kicking it. So, first question, find velocity and acceleration equations. So, notice it does not tell you to do any derivative stuff. It just says, give me velocity, give me acceleration. You've got to know that velocity is the derivative of distance. This is a distance equation. So velocity, we'll call it v for velocity with respect to time, is the first derivative of distance. So velocity is the y prime. If we do the little power rule, that will give us negative 32 t to the first plus, that's an exponent of 1, multiply, you get 37 t to the 0, and then derivative of 3 is 0. Acceleration is the second derivative of y, or I could have called it the first derivative of velocity. They're all the same. You only need one of those in there. So I need to take the derivative of this one here, exponent's 1, negative 32, and then the derivative of 37 goes to 0. And if you are in physics, negative 32 should be a number you are familiar with. Has something to do with gravity. We'll leave it at that. Let's see. Oh, we should have done units. In velocity, this equation is going to be feet per second. And this will be feet per second squared. So B, find velocity at 1.5 seconds. So velocity, just go to your velocity equation and plug in. So the velocity equation is right here. Negative 32 times the 1.5 plus 37. Crank through that on a calculator, you're going to get negative 11 feet per second is your velocity. Okay, based on that answer is, well, maybe not just based on that answer, is the ball moving up or down? Is it still on its way up, or is it coming back down? At time equals 1.5. Well, because it's negative, that means the distance from the ground is decreasing and just getting closer then, so it's on its way back down. Now, is the ball speeding up or slowing down? At 1.5. Now remember, this negative here doesn't tell you it's slowing down, it tells you that the direction of it's coming down. So I told you on the other page there that speeding up and slowing down depends on two things. You need to know what the sign of the velocity is, which we've got, and you need to know what the sign of the acceleration is. Well, the acceleration at 1.5, if you look back, the acceleration equation was a constant, negative 32. It's the pull of gravity, feet per second squared. So because acceleration is negative, the velocity is also negative. Both negative means it's speeding up. You have to look at both of them to answer a speeding up or slowing down question. You cannot look at one alone by itself. Okay. Oh, I need the book. 102. Okay, we've got another displacement